All right, consent. Cool. All right, everyone. Welcome to this workshop on binary exploitation, or as it's often known, PWN, so PWN. First of all, many of you probably don't quite know what binary exploitation is and how it's different from like the other hacking stuff that we do at MonSec. So I think a good introduction would be this particular video, where basically there is an existing game, right? Super Mario World on a computer-like device, right? The SNES. And this guy meticulously, pixel perfect, moves around in the world and causes some glitches where the colors change. But his ultimate goal is to have Flappy Bird inside the game. Basically, the entire idea of binary exploitation is that we become puppeteers of the process. We take over what it is doing and we make it do something it should not be able to do. By the way, I'm happy to have questions throughout this workshop. It's going to be a very interactive workshop, but at this beginning, I'm just trying to hype everyone up. So, right, the game never had Flappy Bird, but by making extremely precise pixel perfect movements, he could override the memory. Oh yeah, it's usually been done by a robot, but this guy did it like by hand. By doing pixel perfect motions and hitting the right blocks and stuff, he made the game into Flappy Bird. Other things that binary exploitation is really cool for is jailbreaking iOS devices. So if anyone ever had an iPhone or stuff like that, you probably at one point heard of or played around with jailbreaking your device. So these basically almost always use some sort of binary exploitation to make some critical part of the iPhone do anything that the hacker wants, and that allows them to then install whatever they want. So maybe I should grab the chat and this particular slideshow. Arbitrary code execution, asks someone. Yes, so the main goal of most binary exploitation is for arbitrary remote code execution, which is basically what the words by themselves mean. You get to choose arbitrary code, so anything, and get it to execute. Right, so in this, now the problem with binary exploitation, it's a massive topic and it's very complicated, and obviously I can't teach everything in like an hour. This particular, so like this check rain exploit used use after free bug. And this is slightly more complicated to wrap your head around, so don't really worry about it. What we'll be doing for a good chunk of today is this exercise which I have made, which I call buffer overthewire. So one of the most common security vulnerabilities that can lead to exploiting the binary to get arbitrary code execution is buffer overflows. But there's more to buffer overflows than just writing an extremely complicated sequence of memory to get Flappy Bird to run. You can just override other parts of memory. So this, to explain what every part of this program here does. So this is a website, right? So this exposes some program as a website. That's like the face. But when you actually run the program on the back end, so on the server, like at monsec.io, the server does some calculations using its code, and it produces this report. Now, for your convenience, I have also included this memory dump, which is the exact memory that you need to be concerned with for the purpose of today, because naturally there's going to be a lot of other data floating around in the RAM, but you don't need to worry about that. So as you can see, if I type in whatever, you understand, some amount of A's, it shows up here. So this memory dump is in the format of a hex dump. So just to explain how to read this if you've never done it before, this left column here is the offset in hexadecimal. Yeah, it's basically the offset. So here is like offset 0. Here is offset 16, right? Because 1, 0 in hexadecimal, and so on. So it's just so you don't have to count all the rows yourself. It's like the line of numbers. And then here are the actual individual bytes. And here is just a convenient ASCII representation of those bytes, if it is possible. So for example, this 61616161 is for these 4 A's. But for example, this 00 and this FF don't correspond to any printable ASCII codes, so they're just dots. Now, in reality, processors aren't going to give you this nice memory dump, but it's just there so it's a lot easier to exploit the program as beginners naturally. For binary exploitation, you need somewhere to start, right? So there's some challenges they can do, and they get crossed off as you do them. So the program detects when it's exploited. Obviously, that's also like an arbitrary thing. So let's have a look. Any questions? No questions at the moment. So everyone, I would like you to go to this website, buffer.monsec.io, and have a bit of a play around. Type all sorts of things into the password and the age, and see what sort of output you get. Cool. Oh yeah, Monash login, getting autofilled, that's a classic. Or some other logins. This is why I use like a semi-fresh browser with not many stuff, because otherwise it's a bit scary. Please don't send like your Monash credentials to this. Like we probably won't capture them, but they might end up with some logs somewhere, so please don't. So the first step to basically a buffer overflow is to see if you can overflow a buffer. And the only way you can really do that is by just sending a lot of data, all right? So for example, if you send, it really doesn't matter how many A's as long as it's like beyond a certain threshold, you'll see that these A's just keep going and they go past the password and then they just keep going, right? So what's happening here, maybe if I get rid of these A's, it'll be more clear. So this is like the, what does it say? Okay, so let's just say, okay, this is the username, this is the password, and this is the age. So let's, 123 is an okay number, 128 might be better. Okay. So the username is here and the password is here. If we put a lot of A's, then you see that it runs into the password. And then it keeps going. So the reason this is happening, because it's not too intuitive, there's like two reasons. First of all, the username field, it improperly handles usernames which are too long. So instead of cutting off the username or giving an error message, the program incorrectly accepts such a large username, but it writes it into a buffer which is not long enough for the username. So we can see that the username would usually only have this many characters. This is 32 characters with some quick maths. Yeah, because 16 plus 16. So if we send more than 32 characters, then it starts running into whatever's next in memory. And in this case, it happens to be the password. Now, the reason that the password isn't overwritten is because it happens to be written to its buffer after the username. So first it gets the username. And even though it overflows into the password buffer, the password gets written to where it should go. So like it's sort of fine there. But of course, the result is not fine. Even if we didn't have this memory dump, we would get such a report. And the password, which is redacted here, is not redacted here. Because now, when the username buffer is read, it is read until we hit a null terminator, a 0 value. And since there's no 0 value between A and password just gets read out. That's basically how buffer overflows almost always work, right? It's just the CPU doing what it always does, but because some memory is overwritten, it does something different than what the programmer intended. Are there any questions so far? No, no questions. So that's this task done. Now I want to get some interaction for the reading another user's username. So given this memory dump, does anyone have any ideas of where we should start looking to get a user's username? Like another user's username, not our own. Just open the chat. Offset 50. Yeah, that is extreme. No, that is, yes, that is exactly what we need to do. Yeah, 50. I thought it was later, but yes, because Alice is at the beginning and these characters correspond to Alice. So we do need to start, we need to get to offset 50 somehow. So let's just send a bunch of A's, right? Just a bunch of A's. Ooh, okay, yeah, that's no good, is it? Alice is no longer there. We happen to override that data. Luckily, this application is extremely resilient and it like refreshes its database every time. But naturally, you wouldn't want someone with a really long username to override some other user's data. So that's bad. But we also didn't achieve our goal of reading another user's username. So that's the thing with buffer overflows. It's usually quite easy to get some bad behavior, like a crash or just garbage data, but you'd really need to craft something to get it to do exactly what you want. Yeah, you can't just send a bunch of A's and suddenly you have remote code execution. You need to send very targeted A's. Well, probably more than just A's, but you get the idea. Okay, so let's try sending a more controlled number of A's. So I just send some A's and I'll just look at the memory dump. Okay, we're getting there. Oh, okay, that's too much probably. Let's take off those. Okay. And we're still not getting to Alice, right? We still can't read it in the report because there still is this null terminator coming up at one point or another. So we need to do something tricky because, oh, what's happening? Okay. So we need to do something more sneaky because we don't want this null terminator, right? And the reason the null terminator is happening is because the thing which takes the input always puts a null terminator at the end of the buffer. I mean, at the end of the data it has written, which is hopefully before the end of the buffer, but it's not in this case. So what can we do? We need to override this null terminator with something. Does anyone have any ideas on how we can get rid of this null terminator? I'll give a hint that it's sort of similar to the password in that we write the password after we write the username. So that's why if we do something like this, right? Now there's no null terminators relating to the username. It's just the password's null terminator then, yeah? So we tried the usernames input. So now we can try the password input. So after overflowing into the password, let's overflow the password. So this might not always work depending on the application because some applications only have like one input, which is vulnerable. But in this case, turns out everything is vulnerable. So let's try that. Yeah, so unfortunately, we are still getting null terminators with the password because, again, the password is a string, and the way that it's often handled, particularly in the C programming language, is after a string, there's always a null terminator put there. So do we have something, maybe something that isn't a string that we can control to be not zero, basically? We just need to be not zero. We don't need it to be anything special. We just need to be able to put a byte that isn't zero where our byte with a zero is. Tim Sylvester on top of it. So yes, we've exhausted these two options. So maybe the age is the only option left. Well, let's have a look at where the age is in this output because I don't see any 123s. Does anyone know what this 123, not 123, 128. There are no 128s here, yeah? Maybe if I make this to 255, you will see it more clearly. And then I'll just go like this. So the age needs to be stored somewhere in this block, yeah? Because logically, the program is going to group information for one user together, yeah? So you have the username and the password, so the age has to be somewhere, probably here, probably not before. And if you play around with the age, 65536 and 65535, you'll see that this part doesn't change. So it's not relevant for our need. But what you do see change are these bytes here. So this is why it's important to not only look at the ASCII output because it doesn't show all the changes, yeah? So here, this age, so if we set it to right? If you set it to something like 5, then it makes sense. It's 5. The highest thing you can represent with a single byte is 255. So that gives you FF in hexadecimal. But then if you go 256, something weird happens. This becomes a 0, and then this becomes all zeros, and this becomes a 1. So why is that the case? Well, perhaps if we go the next, so with 8 bits, we can represent up to 255. With 16 bits, we can represent up to 65535. It's just a number you memorize. And that gives us FF as we expect. But then if we go one more, then suddenly this becomes 0 and this becomes 1. So sort of similarly to how if we do arithmetic by hand, if we do something like 50 plus 60, those are 2-digit numbers added together, but it gives us 110, which is a 3-digit number. So that extra digit needs to be added somewhere. And as humans, the common convention is that the next bigger number goes to like the left, yeah? But most computers do it the other way around. They do what's called little, wait, let's not screw it up. Yes, they do little endian. So if you look up endian in this, then there's like a lot of extremely specific information if you're interested in that. If we look for Intel generally goes towards little endian, and you can see all these historical stuff, but x86, that's the big architecture that's like this laptop runs on and probably most big things run on. Your phone doesn't do x86, so it might use a different endianness. Who knows? It depends on the architecture. But basically, numbers are represented backwards, which is not that intuitive when you first see it. But strings, so basically numbers are represented right to left, and strings are represented left to right. So strings make sense, yeah? Username is in this order, it's correct. But numbers, if we do something like, let me just F12 and get the JavaScript console for some quick hex conversion. If we want a number like OX1234, which is apparently 4660 in decimal, and then we send this, we actually get 1, 2, and then 3, 4. So like the bytes are backwards. The digits in the hex dump are like correct order within a byte, but the bytes are reversed, okay? But anyway, enough of a tangent. If we look at, let's look at the password. So I just add, so this is the last B, then this is A, which is value 10, which means new line. And then we have the null terminator. So if I add a B, everything gets shifted over by 1. Ooh, but then we don't have a null terminator. We just have our 3, 4 from the age. And oh yeah, this happens to be value 4, but that's just a coincidence. So now we've gotten rid of the null terminator because we overrode it with the age. So it makes sense that the program, okay, first it writes the username, then it writes the password, and then finally it writes the age. If it does any overriding in the process, so be it. The computer wasn't expecting the buffers to be overflowed, so it's just going to overwrite the data. It's going to assume those overflows never occurred, and it's going to write the data where it would be if they wouldn't occur. Okay, but now we have these zeros, and I alluded to previously 65536. Well, now we have zeros here, but we have a 1 here. So the best way, and then, so we have 2 to the power of 16 is 65536. And there's 8 bits in a byte. So if we do 24, then we get this number. So let's just send this through. So we get this, which is currently valued this. Yeah, because if we reverse the bytes, then this is what we get. And then we want to get rid of these zeros, right? So we need to change this number to something that isn't 0. So literally anything will do. So I just put Fs and we get this number. Sounds good to me. Cool. And now, as you can see, our password, which would be, okay, so this is the last B, this is the new line for enter. And then this is where the null terminator should be, but this number needs to be represented by 4 bytes. So then we don't have the null terminator, and then we correctly overflow and reach Alice, which we can see in the output here. And this is not working correctly, sad. But it should be crossed off if it was working correctly. But of course, whenever there's a live demo, things can't work completely correctly. But you can see that, you know, we have Alice here. Potentially if I add an extra B and then, right. So when we get rid of the new line because it gets overridden by the age, then the program correctly detects your solution. And all this is the FF bytes here, yeah. And then there's some 01 bytes which you don't see because sometimes bytes can't be printed. And then you see FF again, some more. So lots of weird stuff happening because we're overflowing buffers and we're changing things that we shouldn't be changing. Rightio. Any questions so far? Oh yeah, and if we try to make this number like any bigger, it doesn't actually, it doesn't overflow into like the next byte. So that's just a thing which you can't do generally as an attacker. Numbers are generally represented in a fixed number of bytes. And if you go over that number, then it just loops back to 0 or to some negative number, depending on representation. But you can't buffer overflow if the number is stored as a number, because that's always the fixed size. Why that particular number for age? Yeah, so excellent question. We don't need this particular number. We can do lots of other numbers. Can we? Not that one. Wait, what? Oh, right. Okay, yes, because then we go. No, it should be fine. Hang on. Oh, yeah, because then we get 0 bytes. Okay. Basically, a few other numbers will work as well, as long as their hexadecimal representation does not have 00 in it. So a classic number is OX dead beef. So this will work as well, as there are no zeros in it either, right? So we get dead beef, and that doesn't have any zeros. So then this doesn't have any zeros. So the reading continues until there's a 0, like 00. And that doesn't happen until after Alice. So you can do lots of other numbers which don't have zeros. So OX and then just, so 1 byte, 2 byte, 3 byte, 4 byte. This number will work fine too. Plenty of numbers should work. So if I just increment this by 1, this should still work, right? And I can just keep on incrementing it until the representation gets zeros, at which point it's no longer useful for me as an attacker because I can't read Alice because there's a 0 in the way. So I hope that answers your question. If not, then like ask it again, basically, and I'm happy to explain some more. Thanks. Okay, so I'll assume you are satisfied. Right, the final challenge is making yourself an admin. And now this seems like an unattainable goal at first. So if we just do some normal age, and let's get rid of the buffer overflows for a second to just have a look at what the normal data looks like. So first we have some bytes here, which we don't really know what they do. Then we have the username. So these 4 bytes correspond to these 4 dots. So this is something worth investigating. But then we have the username. We already know about that. Then we have the password. We know about that. We can try to guess that the password is also 32 characters. And that will maybe give us a hint that from this point onwards, we're interested in something. But then let's work backwards. So Alice, the memory for Alice is probably structured in the same way as for us. So there's going to be 4 bytes at the end. I mean, at the beginning of Alice's like data section, which are something. So that would be these 4, which are these 4. And if we look carefully, the only difference is that this is a 1, but the FFs stay the same. So potentially this is an identifier, which is incremented by 1. Then here, these 4 bytes are for the age. So we already tested. If I test the maximum number that can possibly be represented with 4 bytes, which is this, we get 4 Fs here. And then if I try to increment it by 1, we should get back to 0. Right, so we get back to 0. So 4 bytes are occupied by the number. This is Alice's bit because it's like the corresponding 4 bytes here. So then the only part which we don't know anything about really is this. And if we look carefully at our output, we see, well, okay, we are our user. But if we perform an overflow, then it tells us, oh, the user type is unknown and it's this number. So we can just like hex converter or like whatever you like using for converting hex, right? Hex to decimal, now we need it exactly the other way around. So we have some decimal number. Oh, this is represented by 62626262. And what does that happen to be? It happens to be the equivalent of the B's, yeah? So let's just try to find where we were. Okay, so this is where Alice used to be. Okay, here was what we were investigating. Okay, so that makes sense. So let's do a more targeted overflow of just those bytes, just to prove our point. Let's get rid of this. I can also zoom in. Right, and as we add and remove B's, we see that the number is changing. So for example, now it's 2658. So let's chuck it here and we get A62, which if you pad it to be bytes has a leading 0. Zero A 62. Right, so this is the number here. This is the number responsible for identifying what type of user we are. Now, how do we set it to what we want? So if we wanted it to be 62626262, then, I mean, our job is done. We just send a bunch of Bs and it's all good. But this number isn't very interesting. Let's try and set it to something specific. So there was 1 before. Let's try and set it to 2, for example. So first, let's just be precisely at the beginning of the number, which would be here. Right, so for example, now we've got OA, which is new line, which is value 10. Cool. And now the way they can send arbitrary bytes through this form isn't through this form, it's by modifying the URL. Now there's lots of other ways of doing this, like using the web developer console here, or using some proxy like Burp Suite. But for today, the URL will suffice. So now our Bs end here. So if we want to control the entirety of these 4 bytes, we need to, well, send 4 bytes. And the way we can do that through the URL is by percent encoding what bytes we want. So we have 4 times the byte of zeros, and let's make this one 2. So now we get unknown type 2. And then we can keep on changing it, and we get all sorts of results. And we can keep going, and we see, okay, so 10, which is 16, gives us 16, still an unknown type. And then at this point, you have sort of 2 options. You can either brute force a bunch of numbers, which is doable, but you probably want a script to do it. Or you try to find what the admin's value is, right? And if we look at Alice, we see that they have, okay, a username, the password, and then, okay, so after 32 characters, then they obviously have the last 4. Not obviously, what's that for? Don't worry about that. And then there's like this @ symbol, which sort of stands out like a sore thumb. So let's look at the bytes here. Oh, okay. So there's these 4 0 bytes and then just zeros. So potentially this is something worth investigating. So we can, okay, do like 4 0 here. Ooh, 4 0 corresponds to an @ Yeah, that makes sense. But here we still have the 10. Well, if we look at every group of 4 bytes, we see, okay, it should be like 4 0 and then 3 0 bytes. So that's what we can do. 4 0 and then 3 0 bytes. And by doing that, we have successfully convinced the program that we are an administrator. Cool. So how did we exactly do this again? Right, we sent some malicious password, which was longer than the allowable password, and it overrode some other memory. And it's very easy to make this memory like garbage, so just some random value which is not useful for the program, which either causes it to crash or show weird results. But if we craft our input in a very, very particular way, then we can get it to do exactly what we want by overriding that memory with precisely what we want. Right, so now is an extremely good time for questions, because this is the last we'll be seeing of this buffer application for today. If you didn't manage to do the exercises during this time, that's fine. This buffer.monsec.io, this is up 24/7. You can play around with it whenever you want. In fact, it is possible that it's open source. I'm not sure if it's released. No, I might release the source code for this later, but basically, you don't really need to worry about it too much at this point. Just the idea of overriding some memory which was for a particular purpose, and you override it with something else that you want. How could you typically get a memory dump of a program to be able to apply this? Right, so unfortunately, this is a question about how realistic this attack is. And this attack is extremely unrealistic because no web application is going to give you a memory dump. Because not only does it require the programmer to be like stupid, it also requires them to be not lazy. And that's an extremely rare combination. Usually programmers are lazy, so they're not going to be implementing a memory dump. Now that's where the next step sort of comes in. How can we actually exploit programs which are designed to work quite correctly, like they don't give a memory dump of themselves? And for this, I recommend the Narnia war game on Overthewire. So conscious of time, well, we have almost 15 minutes, so that's all right. The Narnia war game teaches the basics of binary exploitation in a more practical environment. It's still not 100% practical. You're not going to be able to hack an iPhone with this because it uses some slightly outdated software, but it is an extremely important stepping stone to be able to, right, go from this application to be able to hacking stuff on Narnia, then the next step, and then the next step, and then you can be elite hacksaw and hack iPhones, basically. So this is another good step. So I'll run through, I guess, a typical workflow for hacking an application which doesn't give such a memory dump by itself. So the instructions for Narnia say that we SSH to this server with username 0, password 0, and SSH port 2226. So it depends on what sort of operating system, etc. you have. Ooh, not good. How the SSH command is going to look, but basically you got to log in as the user Narnia0 to this server on port 2226. Okay, Narnia0, cool. And now this server, again, it's designed to be hacked. So it's not like you're doing anything illegal, but you're also not doing anything revolutionary, unfortunately. It comes pre-installed with some tools, or alternatively, you can download the binaries to your own machine and play around with it there and then exploit it on the remote side. That's the most common thing, because it's no good hacking yourself, because like I own this computer, right? I can just do sudo whatever and I have a full remote code execution. That's not useful. What's useful is persuading an application somewhere else to do what you want it to do. Now the actual challenges are all in /Narnia. And if you look at the output, the way it sort of works is if you manage like Narnia0, you can run it as Narnia0, but it becomes Narnia1. So it gets the privileges of Narnia1. So that means once you control the Narnia0 executable, you become like a higher user. So that's how you progress. Now let's just run this program, Narnia0, and it says, oh, change Val's value from 41414141 to dead beef. So if we just do like hello, then it says, well, the value is 41414141. So you suck, you didn't really get anywhere. Now we can use like a text editor or like less, just something to read the source code of this program. Oh yeah, sorry. So due to the way my terminal is set up, I need to do this step, term equals x term. Don't worry about that. It's just to make things look sane. Now, basically the way the program works, okay, it creates some value, which is of type long, which is just an integer, 41414141, and it creates a buffer of 20 characters. Then it proceeds to read 24 characters. So that's a programming mistake, which means there's going to be an overflow of 4 bytes. Rightio. So if we try doing something like echo and then -e so that it interprets \x correctly, we can do, okay, let's do dead beef. And then let's do 20 of some character. We don't care. We just need to fill those 20 characters. So I'll just do 5 A's. And then I'll paste it. So, okay, we have 20 A's and then we have dead beef. This is just a way of telling Echo, I actually want the byte value DE rather than the characters DE, yeah? And then we can just send it over to Narnia 0. Ooh, okay. This isn't exactly what we wanted. It looks sort of like dead beef, but it's not. Does anyone understand why this could be the case? We sent dead beef, but now it's sort of like weirdly jumbled up. You can either send a chat message or read in backwards. So what exactly do you mean read backwards? Wrong endianness. Yes, exactly, Leo. So again, the endianness comes up because sort of like in the buffer exploitation exercise here, numbers are stored backwards, right? That's a common theme. It's not like sometimes stored backwards, sometimes forwards. On x86 processors, numbers always backwards. So we want dead be what? Beef. No, okay. So that's dead beef with the bytes reversed. And we don't get the way off message, but we also don't get anything else. Now, there's a very annoying reason for this. And that is that when we send this input, then Echo says, okay, that's the end of the input. And then the program says, okay, that's the end. So you're done with me. And then it just closes the program. Whoa, that is not good. Let's not do Vim. That doesn't matter. We're not editing the file anyway. What should happen if the value is dead beef is that we execute a shell. The way we can do this, let me just make a temporary directory that we can actually write to. So that's a disadvantage of this server. You can't actually write like almost anywhere. That's not a limitation on your own machine, right? You can write files wherever the hell you want and you can screw up everything. But on this machine, it's a bit more restricted. So this is just a way of making a temporary directory. So if we echo this to a file like attack, then we can do the exact same thing as our echo by doing this. Ooh. Okay. So again, we get the nice output, but we can't exactly do anything with the shell because the input is immediately terminated when this text terminates. So the solution to this is horrific. And it takes like ages to understand exactly how it works. But if you if you concatenate attack with the standard input, which is represented by a dash, then everything works fine. So just trust it for now. You'll understand it at one point. But basically here, if we do the who am I command, it says Narnia 1. If we run our exploit and we do who am I, we get Narnia 1. So that's how you attack something more realistic, not like a web application which dumps its memory. But there's still the problem of, well, what if we didn't have, what if we didn't have this source code? And that is, no, not the binary, .c. Okay, right. So there's the actual compiled program that the computer can run, and there's the source code, and you don't always have that. And the way to get around that is basically reverse engineering, and there's lots of ways to do that. But I'll just quickly give a demo. Unfortunately, we're running out of time, so it's going to be real speedy. But the GNU debugger can, well, debug programs, including giving you memory dumps if you so desire. So the problem with GDB, and you're not going to be told this in your Monash unit, but GDB is ancient software and it's terribly difficult to use. Luckily, people have made scripts which make it usable. So if I go user local pwndbg and then gdb init.py, this command should install pwndbg so that things are a lot more pretty. Please. Yay. Okay, so we get colors, and that's like one of the main features of pwndbg. We get lots of colors. That's epic. Now, if we just, like, the main function is like 99% of the time called main. So if we do this as main, we get a bunch of like stuff. And I'll just skip over a lot of like steps in the interest of time. Let's say that we want just before the if statement. So that happens to be done by a comp instruction. We compare something with OX dead beef. Yeah, that sounds about right. So you want to tell the program to pause at this point. And that's what a debugger lets you do. So let's break at this point and then run. Okay, so we're running our program. And now let's do a message like hello. Yeah. Okay, and we hit the breakpoint and pwndbg spits out a lot of information, some of it which is useful, some of it is not. So there's the registers, don't worry about those. There's this assembly, which is, well, just this, but with colors. And then there's the stack, which we are interested in. But although this is useful to get a brief overview, it's not as clear as a hex dump, in my opinion. And the way you can just get a hex dump is, well, hex dump. And if we have a look, this is exactly the sort of thing that was in this buffer.monsec.io. It's, well, the offsets and the byte values and the text representation. So this is what we can see, right? This is the bytes hello, and the 414141 are here. Yeah. So then we could count and be like, okay, 4, 8, okay, this is 16, 20. So we need exactly 20 bytes before we overflow here. And in fact, if I rerun the program, yeah, let's rerun the program. So I think if I run again, cool. So we do like 5 A's, and then let's just send 4 Bs, and then we hex dump. Then we see that we changed these 41414141 into Bs, which is 62626262. And if we continue the program, then it tells us way off. Yeah, so that's as expected. Now, this dump is not exactly what the server has. Basically, whenever you put thing into a debugger, things are a tiny bit different. But they're usually very, very similar, so that if you can exploit something through the debugger, you can then run basically the exact same thing, but on a remote machine. So if we do run and okay, and we do attack, I think this should do it. Cool. And at this point we do a hex dump. Cool. Right, so this is just another operator, so that we don't pipe something into the program, we like put it into it, but like backwards, don't worry about it. But that's our attack, so we've got the 616161 and the dead beef backwards, and then we run it, and things are okay, except the debugger then gets confused. Sorry, it's because I did run again. What you actually want, after inspecting the memory and being like, yep, this looks good, then you can say, okay, continue the program from where I left off. And then the debugger gets confused because a new process, that is the shell, like bin/sh, gets executed. Right, so just before I wrap up, are there any questions about, well, anything I've done today?
I just have a question. If you go back up a bit to the memory dump. Yeah. So there's like 5 A's here. Well, after the 5 groups of A's, usually there will be like the capital A's there, right? Like in that C code, is it just so happens to be like first you declared that 20 character array, so it gets set at like a 0 offset. Then next you declared what was it called? Then you declared the val variable, and then it just gets put right after. Is that just how it's done in computers? Is that why?
So that is a fantastic question.
Yeah.
The answer is, in this case, if you get this program and you compile it with GCC, so the GNU compiler, you will always get this sort of behavior, unless if the values are completely optimized away, basically. So if we look at the source code, first we have the value, then we have the buffer.
Right.
The way GDB stores things on the stack, which is what we were playing around with just then, is always exactly backwards. So we have like the 4 A's, and then before that we have the buffer of 20 characters. However, this is not guaranteed to happen, depending on what the compiler decides to do with it and on your version of the compiler.
Yeah. So this happens to work in this setup based on how they set up the Narnia server then?
Basically, yes.
Okay.
And again, you're thinking, oh, well, this is unrealistic. And yes, to some degree, it is unrealistic. But there is, no, not in this particular binary, but in a lot of cases, even if the variable is somewhere else, you can, with enough trickery, you can do anything, basically. Yeah. If there's a security vulnerability and you can override something that's critical to the program, then you can do anything.
Yeah. Cool. Thank you.
So obviously I just went through Narnia 0, and there's more levels than that. So I strongly suggest people, if they are interested, obviously, this is not everyone's cup of tea, playing around with bytes like this, naturally. But if you're interested in this, then I strongly recommend the Overthewire Narnia game. So overthewire.org/wargame/Narnia, which I sent in the chat at least once. But there it is. Maybe I didn't send it, but at least once now. Because it can really teach you about these tactics could get you basically exploiting everything like 20 years ago. But there's this constant cat and mouse game where the security people slap on something which sort of fixes the problem, but not 100%. Because the root cause is that programmers are lazy and they incorrectly do things like make a buffer of size 20, but then read 24 characters, or worse, read many more characters. If Narnia is not enough for you for some reason, then there's ROP Emporium. Now, ROP Emporium is probably the best resource for learning modern exploitation. So this stuff will work on modern devices with modern security protections enabled. So a lot of Narnia is sort of like where security was 20 years ago. Once you can do ROP Emporium, you can break binary security today. So that's like the end goal, which I hope many of you will reach. So that's it from me, but I'll stick around for a little while if people have questions and they don't want to ask it while it's recorded, which is fair enough.